Welcome back. This is Mr. Anderson from Math 130, Keller Community College Statistics class. We're going to be doing today section 8.3, doing a t-test for mean hypothesis testing. The last section we covered z-tests, but when our sample size is less than 30, we're going to be doing t-testing using the table F, which is in the back of the book, but I also provided a copy of Table F on this worksheet, so if you printed it out from my Moodle page, you can use it, and we'll see that up on the screen here. A t-test looks a lot like the z-test, except there's one slight difference. When we have our sample size less than 30, we're going to have S for our standard deviation instead of lowercase sigma, and everything else stays the same, but on our table F, we have to be aware of something called the degrees of freedom. And the degrees of freedom is always one fewer than the sample size that we have. So if you have a sample size of 12, your degrees of freedom are 11. If your sample size is 30, technically 29, your degree of freedom will be 28. Now there are 5 steps for hypothesis testing, and these are similar to the 5 steps with the z-test. You're going to start by stating your hypotheses. And then after you state your hypotheses, you're going to find your critical values from table F. Where normally we'd use table E for the z-test, we're going to use table F. Then you compute your test using your standard deviation, lowercase s. Or if you're using your graphing calculator, it'll be uppercase S. And then you're going to make your decision to reject or not reject. To reject or not reject the null hypothesis. And then in step 5, you're going to summarize your results. Alright, so there are your 5 steps, just like the 5 steps before in the z-test, except that we're going to be looking at the table F for our critical values, which will be based on the degrees of freedom. Alright, you may want to pause this because I'm going to move this down. Alright, so for our 3 examples, we're going to have 2 examples using the t-table, the t-table just traditionally, and then we're going to spend our last example looking at percentages, or the p-test. Alright, bloop. An investigation claims the average numbers of infection per week in a hospital is 16.3. A random sample of 10 weeks had a mean of 17.7 with a standard deviation of 18%. Can we be 95% certain that 16.3 is correct? So we're going to have an alpha of 0.05, and we're going to look to see if 16.3 is right. So you may want to pause this here to try to guess your null hypothesis, your alternative hypothesis, and then tell me what kind of tail test this is. So that's the first part of step 1, is to write your hypotheses, and then probably it's a good idea to figure out what kind of tail test you have. The null hypothesis is that the average is 16.5, and the null hypothesis, or the alternative hypothesis, is going to be that mu is not equal to 16.3. That's from the last sentence. Can we be sure that 16.3 is correct? So our alternative hypothesis is it's not going to be. And this makes this a two-tailed test, because since we can have, we're looking at above and below this value, we're going to be looking at the left and right tails. Now, we have our alpha is given in the problem as 0.05. We have the degrees of freedom being 1 fewer than our sample size, so 10 weeks minus 1 equals 9. So we have 9 degrees of freedom there. And so what we're going to do is we're going to go to our table and we're going to take a look at the t-value. So look where the degrees of freedom equals 9 and go across, and now here's the important part. And this is going to disappear, but I want to show you where we're going to see this on our table here. So we're looking where our degrees of freedom is 9. So let me get the pen back up here again. So we're looking at 9, and we're going to go across the table, and remember we're choosing a two-tail test, and that two-tail test is going to want an alpha of 0.05. So we're going to look and we're going to find that the value here, straight across and straight down here, is going to be 2.262. But since it's a two-tailed test, we want positive 2.262 and negative 2.262 to be our critical values for the critical region. Now, unfortunately, when I go back to my problem, that's gone. But let me just put down the important information again, just so we have it up there, so when we finish the problem we can see it. Our null hypothesis, whoops, I gotta click on the right thing here. Our null hypothesis, darn it, our null hypothesis is going to be, sorry, having some pen problems here, 16.3. Our alternative, this is where mu is equal to 16.3. Our alternative hypothesis is where mu is not equal to 16.3. We have our degrees of freedom being 9, and we have our critical values for our 5% at plus or minus 2.262. Now we're going to compute our 17.7 minus 16.3 divided by 1.8 divided by the square root of 10. Now if we compute that out correctly on the calculator, we get 2.46 positive. So if we analyze that in step 4, our critical values were positive and negative 2.262. So our question is, was our test value inside either of these critical regions? And the answer is yes. It was over here at 2.46, which is higher than 2.262. So 2.46 is greater than 2.262. Therefore, we are going to reject the null hypothesis. That we found out that the infections per week in this hospital is a really, really strong indicator because it was higher than the two-tailed test with a 5% certainty. Woo! Right there. So we only had a 5% chance of getting this test wrong. So this is a very strong test. So we're definitely rejecting the null hypothesis. This is significant. Okay, moving down to the next problem here. All right, and what we're going to do here is a calculator problem. And I think I'm going to do the calculator problem first because I want this to stay on the screen. So I'm going to grab my graphing calculator here. And here we have a small data set. Let me turn the calc on. Second plus 712, just resetting the calculator back to its original position. We've got a random sample of 8 districts, and we're talking about accusing a school district that the average salary of the substitute teachers was less than $60 per day. So we're going to type this data into our calculator, and we're going to get some information here. We got $60, and just one step at a time, 56, 60. I'm not using my number pad, so this is going a little bit slower here. Okay, enter that in. So those are our 8 pieces of data entered. You can scroll up and check your data just to make sure you didn't make any typos, as I'm doing now. All right, looking good. All right, now to get the average that we're going to need and our standard deviation we're going to need, because I want to round any of my money calculations to the nearest penny, we're going to go stat, right, 1, and then enter. Okay, so it looks like my average salary is $55.88, and our standard deviation, we're going to use the uppercase S here, which is $5.08. Okay, I'm going to freeze that and take it to my screen draw here. So my null hypothesis is that probably the school district is not going to want to be called a cheapskate, so they're going to want to assert that the average is $60 a day. The educator is claiming that the school is being cheap, is going to say, no, you guys are definitely less than $60 per day. And they're choosing a pretty weak alpha of being this a one-tailed test, the left-tailed test. Being that this is a left-tailed test, and this being 10%, you're going to find that this is pretty loose in terms of your numbers. So what we're going to do here is put down our alpha being 10%, 0.10, and our degrees of freedom is going to be 7, because we only had 8 pieces of data, so 8 minus 1 is 7. Now, to not lose any of this, I'm not going to go to my table, but I want to say that if you go to your table, you've got to look up your critical value at the left side, which is 7. Now here's the tricky part. This is a one-tailed test. This is a left tail, one-tail test. So you're going to choose your first column. And your first column is going to say to the very, very right, this 1.415. Now you might say, but that's under 80% and we want 90%. But remember, you're choosing a one-tailed test. So you want 1.415 for an alpha of 10. So you're technically choosing an 80% confidence value, which means you have a 20% chance of making a mistake here. Now, since this is a left tail, you also have to choose your confidence value of being, or critical value of being, a negative 1.415. So if we're going to prove that this school district is being kind of cheap, we're going to want our test value to be less than 1.415. So here comes the test. We found our average was $58.88. So far so good, because we see the average is less than 60. Subtracting it from our 60, we're going to divide this by the standard deviation, which in this case was $5.08 divided by our sample size, which is 8. Now if we perform all of those computations, we're going to find out that our answer is going to be hold on a second here. I got the wrong side here. Is going to be negative 0.61. Now that's bad news for us, because if we were trying to show that the school district is being cheap, we were hoping that that was lower than our critical value of 1.415. But what we found out is, since that is this at negative 0.61, here it is. It's not inside the critical region. Negative 0.61 is greater than negative 1.415, which means that we're not going to reject the null hypothesis. We cannot prove that that school district is being cheap because we chose a very loose with an alpha that would give us the left side of that table F. We have no reason to say that this school district was being cheap at all, according to this the samples that we ran. All right, this is all going to go away.